Picture this. You are standing in front of a massive, state-of-the-art CNC machine.
Oh, yeah, just right on the factory floor.
Exactly. And you can feel that heavy bass thrum of the motors vibrating right through the soles of your shoes.
It's an incredible amount of power.
Right. And behind the thick, blast-proof safety glass, there is a solid block of really expensive steel. It's being absolutely blasted with high-pressure coolant, and a specialized deep hole drill is carving its way into the dead center of that metal block.
Just, doing what it's designed to do.
Yeah, from the outside, walking past on the floor, everything looks perfectly fine. I mean, it sounds like a normal Tuesday. But what you can't see, hidden deep inside that dark flooded hole, is a silent countdown to destruction.
It really is a countdown, yeah.
Because if the person running that machine isn't paying absolute mathematical attention to invisible forces, that tool is going to fail. And the expensive metal part is going to be ruined, and the entire system could violently tear itself apart.
It's an incredibly high-stakes environment. And, the most dangerous part is that the actual cutting action is entirely hidden from view.
You literally can't see it happening.
Right, you can't. So today's deep dive is taking us right into that invisible world. We are unpacking a highly specific, densely detailed technical guide on how to adjust cutting parameters based on CNC deep hole drilling toolware.
It's quite the manual.
It is. At its core, this source is a manual for machinists. It's about saving drill bits and protecting highly expensive metal components.
Yeah.
But the deeper you read into the physics of what's happening, you realize it is fundamentally a masterclass in how complex systems fail when we ignore them.
Yeah, because this isn't just about metalworking, is it?
Not at all.
It's about what happens when we ignore small, unseen degradations in any system we rely on. I mean, the human tendency is to just press start, walk away, and assume everything will run perfectly forever simply because it ran perfectly yesterday.
Oh, absolutely. And the source material explicitly warns against that exact mindset. This guide proves that survival in a high-friction environment requires tiny, proactive, highly calculated mathematical adjustments.
You can't just set it and forget it.
Exactly. Relying on blind momentum guarantees a catastrophic breakdown. We just have to constantly adapt to the wear and tear we cannot see.
Okay, let's unpack this violently expensive domino effect of ignored wear.
Let's do it.
Because before we get into the precise numbers and the exact adjustments needed to save a tool, we really need to understand the chaos that happens when an operator just presses the green button and ignores the tool completely.
Right. Why do we even care about tweaking these tiny numbers in the CNC program?
Yeah, and the text talks extensively about what happens when a tool gets dull. Honestly, the most relatable way I can visualize this is trying to slice a delicate, overripe tomato with a completely dull, flat butter knife.
That is a brilliant way to picture it, actually. What's fascinating here is that the underlying physics are surprisingly similar.
Wait, really? Between a tomato and a block of steel?
Yeah, I mean, when a deep hole drill is working perfectly, it's shearing the metal. It's getting under the material and peeling it away in clean little chips. But over time, the sharp edge of the drill degrades.
It gets dull.
Right, it becomes rounded off and flat. Just like your butter knife on the tomato, it stops slicing and starts pushing. It starts rubbing heavily against the solid metal block.
Oh,
And when steel rubs heavily against steel at thousands of revolutions per minute, the amount of heat and friction generated is terrifying.
and the numbers they provide on this are staggering. The guide states that cutting forces jump up by 30% very fast when this rubbing starts.
30%.
Yeah, 30%. That's a massive spike in pressure out of nowhere.
Think about the physical resistance of walking waist deep through water in a swimming pool. You can move smoothly, right?
Yeah, sure.
Now imagine that water suddenly turns into thick, heavy mud. The effort required to take a step instantly spikes.
Oh, wow, yeah. You'd be stuck.
That's exactly what the machine spindle is experiencing. It's suddenly fighting 30% more resistance, pushing against a wall instead of cutting through it. And because of that intense friction, the heat cannot escape.
Because the chips aren't carrying it away.
Exactly. The metal shavings, the chips are supposed to carry the heat away. But when you are rubbing instead of cutting, the text describes a scenario where the extreme heat literally melts the tool into the workpiece.
Melting solid steel and tungsten carbide together through sheer friction. That is wild.
It really is.
And you can actually smell this happening on a factory floor, right? Like that sharp, acrid smell of vaporized coolant when the heat gets totally out of control.
Oh, absolutely. Operators know that smell instantly.
And the dominoes just keep falling from there. Because once that tool point starts wearing down and melting, it loses its perfect geometry.
Right. A sharp drill point is engineered with highly specific angles to center itself as it pushes deeper into the hole. It acts like a guide rail.
But a melted one doesn't do that.
No. A worn, dull drill point changes shape completely. It loses its centering ability. The source material notes that it begins to wander off the center line.
So it's basically drunk walking its way through the metal block.
That is exactly what it's doing, and that wandering ruins the hole dimensions entirely.
It makes it too big, right?
Yes, the hole loses its perfect microscopic roundness. The diameter grows too large, and the operator has completely lost control over the final size of the product.
Which is a massive deal. I mean, if you're manufacturing a titanium landing gear strut for an airplane or some specialized medical device, a hole that is slightly out of round doesn't just mean a minor defect.
Not at all.
That means a part worth thousands of dollars goes straight into the scrap bin.
And the surface finish drops significantly alongside the dimensions. Because the dull tool is violently squeezing the metal rather than peeling it, it actually tears the walls of the hole at a microscopic level.
Tearing solid metal.
Yeah. You go from a beautifully smooth, mirrored surface to a rough, torn, jagged texture. Customers will instantly reject those parts.
But the destruction doesn't even stop at the workpiece. The guide outlines the final stage of this domino effect, and it's the machine itself taking the hit.
Right, the vibration.
Yeah, the uneven wear causes the whole machine to shake. The metal chips, those shavings we mentioned that are supposed to evacuate cleanly out of the hole, they get stuck, they start packing in.
It turns into a nightmare in there.
It does.
Hmm.
So now you have a dull, wandering tool surrounded by a concrete-like mixture of stuck chips, trying to violently push its way through a solid block of metal.
Which violently overloads the machine's spindle.
And the spindle's important, right?
Oh, it's the ultra-precise, incredibly expensive heart of the CNC machine that rotates the tool. Under this immense 30% higher pressure, a long, deep hole drill will flex, bind up in those packed chips, and simply snap off inside the heavy metal block.
Just break right in half.
Yep. The tool is ruined, the part is garbage, and the operator has potentially destroyed a spindle that costs tens of thousands of dollars to rebuild.
All because an operator pressed start and assumed the system would take care of itself.
Exactly.
So since the consequences of neglect are so physically and financially destructive, how do we actually prevent it? Logically, you might think the solution is just to swap in a brand new tool constantly.
That would be the assumption, yeah.
Right, because a brand new tool is invincible. It's perfectly sharp out of the box. But the source reveals something totally counterintuitive. The journey to saving the machine actually starts with treating a freshly unboxed tool as highly fragile.
It's so true. The initial wear phase demands a mindset that completely contradicts human intuition. You do not unleash a new tool at maximum power.
It reminds me of buying a stiff, brand new pair of really expensive leather dress shoes.
Oh, that's a good comparison.
Right. You don't take them out of the box and immediately run a marathon in them on day one. If you do, you're going to destroy your feet with blisters and probably crack the stiff leather.
You'd ruin them.
Yeah. You have to walk around the house in them first. You wear them for short bursts to soften them up, to break the material in gently without destroying the structure.
And that break-in period is the exact mechanical strategy the guide prescribes for a new deep hole drill.
But the drill is made of metal, not leather.
True, but even though the factory grinds the tool to a beautifully sharp edge, if you look at that brand new edge under an electron microscope, the text notes you would see tiny, rough metal bumps and microscopic burrs all along the cutting line.
Like little microscopic jagged mountains on a brand new, expensive drill.
Exactly. And those tiny, sharp peaks are incredibly brittle. If an operator slams a brand new tool into solid steel at maximum programmed speed, the shock value is just too high.
They just snap off.
Yes, those microscopic bumps will shatter and chip off immediately. The perfect edge is ruined before the tool has even drilled its first full hole.
So you really have to ease it in. You have to condition the tool.
The operator is required to employ a highly precise mathematical strategy for this initial phase. To flatten these rough microscopic peaks safely and create a smooth, unified cutting edge, the guide instructs them to drop the cutting speed by 5 to 10%.
Okay, so if your normal programmed cutting speed is, say, 100 meters per minute, you are intentionally dropping it down to 90 or 95 meters per minute for those first few cuts.
Right. Dropping the rotational speed reduces the impact shock, allowing the edge to smooth out safely. And the feed rate, which is how fast the tool is physically pushing forward into the solid metal, also needs a slight reduction.
How much of a reduction?
The text suggests dropping the feed rate by 3 to 5%. So a feed rate of 0.20 millimeters per revolution drops down to 0.19 millimeters per revolution.
It's such a tiny, seemingly insignificant adjustment. I mean, we are talking hundredths of a millimeter here. It's practically invisible to the naked eye.
It is invisible, yeah.
But it prevents those microscopic bumps from snapping off.
Okay.
Now, there is one parameter the guide points out that you absolutely do not change during this break-in period,
Oh, the depth of the cut. That stays exactly at the programmed maximum.
which feels totally weird. If I'm slowing the rotation down and easing off the forward pushing force to protect this fragile new tool, shouldn't I take a shallower bite of the metal too?
You would think so, but the physical mechanics of the tool dictate otherwise. The text explains that this initial fragile wear is isolated entirely to the extreme microscopic edge of the tool.
Okay, just the very tip.
Right. The overall structural integrity, the thick web of the drill body itself, is at its absolute peak because the metal hasn't been fatigued yet. It can handle the leverage of a deep cut perfectly.
So you're just polishing the edge.
Essentially, yes, the operator only needs to reduce the speed and the pushing force slightly to burnish that edge.
Okay, but wait, let me put my factory manager hat on for a second.
Yeah.
So what does this all mean? If I have to constantly baby this machine and slow it down to save the tool, aren't I just bleeding money?
That is the eternal conflict in manufacturing.
Right, because cycle time is everything. Every second that machine isn't running at max capacity, I'm losing profit. Why not just redline the machine, run it as fast as the motors will spin, burn through the tool, and then quickly swap it out when it dies? Isn't raw speed always better for the bottom line?
If we connect this to the bigger picture, pushing for raw speed while ignoring tool wear is the fastest way to bankrupt a machine shop.
Bankrupt? That sounds extreme.
Well, the source material addresses this economic reality indirectly by focusing on the catastrophic outcomes. Saving 3 seconds on a drilling cycle is economically meaningless if the end result is a destroyed $10,000 block of aerospace titanium.
Just because a red line tool wandered off center.
Exactly.
Okay, yeah, that makes sense. The cost of the scrap part massively outweighs the fractions of a penny saved on cycle time.
Consistency and controlled quality generate profit, not uncontrolled speed. And understanding that brings us into the longest phase of a tool's life.
What the guide refers to as normal wear.
Yes. Once those microscopic bumps are safely smoothed out, the tool settles into a rhythm. The wear rate plateaus and becomes very predictable. But the text makes a crucial distinction here. A predictable system still requires active management.
Because constant heat and friction are still in there, slowly eating the metal away at a microscopic level, cut after cut, hour after hour. It's a marathon now.
Exactly. Just like a marathon runner who has to adjust their breathing and pace as they fatigue, the operator needs a new strategy for the tool. They cannot rely on guesswork or a feeling.
So what do they rely on?
The guide provides a highly specific, measurable visual trigger for this phase. Operators must physically inspect the tool and look for a flat wear mark on the cutting edge. When that flat mark reaches exactly 0.1 millimeters, intervention is mandatory.
0.1 millimeters. That is incredibly tiny. How does an operator even measure that in the middle of a messy, oily factory floor?
Modern CNC machines often have optical tool presetters, lasers, or high-definition cameras inside the machine that can measure the tool geometry automatically between cuts.
Oh, so the machine does it for them.
Or, if they don't have that, the operator pulls the tool out and puts it under a specialized magnifying scope on a workbench. The measurement is exact.
Wow.
And the moment they see that 0.1 millimeter flat spot, they have to drop the cutting speed again, this time by 3 to 8%.
So if you were running your marathon pace at 80 meters per minute, you drop it down to 76.
The specific reason, according to the text, is to control the rising cutting heat. That tiny 0.1 millimeter flat spot acts like a brake pad.
Oh, because it's rubbing again.
Yes, it is generating significantly more friction than a sharp edge, which translates directly to heat. Slowing the rotation cools the tool down and prevents it from thermally expanding and binding in the hole.
And the feed rate? Do we drop the pushing force again?
The feed rate drops by 2 to 6%, so moving from 0.15 millimeters per revolution down to 0.14.
Just another tiny tweak.
Right. A duller edge requires more physical force to push through the metal. By lowering the feed rate, you decrease the mechanical pressure building up on the spindle.
What about the depth of the cut this time? Because, the initial break-in phase, we left the depth alone because the tool was structurally strong. Do we leave it alone now that it's fatigued?
This is where the guide introduces a fascinating caveat that depends entirely on the human element,
The human element.
specifically the customer who ordered the part. The engineering drawings dictate the strategy. If the customer requires high accuracy, meaning incredibly tight tolerances and perfect straightness down the hole, then the operator must reduce the cut depth by 0.1 millimeters per pass.
Ah, I see. Because taking a slightly shallower bite puts less physical bending stress on the shaft of the drill. It stops the tool from flexing and wandering, which keeps the hole perfectly straight.
Exactly. The operator is intentionally sacrificing a tiny bit of material removal speed to guarantee perfect accuracy.
That makes sense.
However, the text notes the inverse is also true. If the customer's rules are loose, if high accuracy isn't strictly required for this specific hole, maybe it's just a clearance hole for a bolt, then the operator can maintain the original cut depth to keep the cycle time as fast as safely possible.
So it's a constant mathematical negotiation between speed, heat, and precision.
Always.
But here's where it gets really interesting. Because despite all these incredibly careful micro-adjustments, the 5% drop here, the 0.1 millimeters there, every single tool eventually reaches the end of its physical life. You can't beat the physics of friction forever.
No, you really can't.
And knowing the exact moment this happens is the boundary line between a routine 5-minute maintenance swap and a completely destroyed machine.
We are crouching into the severe wear stage. And the transition from the marathon of normal wear into severe wear is not a slow, gentle curve that gives you time to react.
No.
It is a cliff.
And the guide describes a massive, undeniable sensory shift when you fall off that cliff. Up until now, this wear has been silent, hidden completely inside the metal block. But when severe wear hits, the machine violently lets you know.
It's impossible to ignore.
The text describes a screaming drill, heavy shaking that vibrates the floorboards, a loud, terrifying grinding noise.
It is the auditory and physical signature of catastrophic failure happening in real time.
This isn't like a check engine light on your dashboard that pops on. You think, it's probably just a sensor, I'll take it to the mechanic next week.
Oh, it all.
This is the engine actively seizing, shooting sparks out of the hood, and catching fire while you're driving on the highway.
This raises an important question, though. What must an operator do the exact second they hear that grinding, screaming noise?
What does the guide say?
The source material leaves zero room for interpretation. You stop the machine instantly.
You slam the big red emergency stop button.
You cut the power immediately. You do not try to tweak the feed rate in the computer.
You don't try to limp through it.
No. You do not try to slow the speed down by another 5% to limp through the rest of the cut. The guide explicitly states that adjusting parameters will never save a dying tool at this stage.
Because at this point, you aren't dealing with normal wear anymore. The text says it transitions into aggressive melting wear.
Exactly. The cutting edge isn't just flat at this stage. The structural integrity of the tungsten carbide is failing. The edge is actively peeling and breaking off.
Oh, that's bad.
Very bad. The tool is literally friction welding itself into the workpiece. Pushing a dying tool even 1 millimeter further guarantees you will destroy the expensive workpiece, and that heavy shaking will permanently damage the precision bearings inside the spindle.
So you hit the E-stop, you wait for the spindle to spin down, you open the heavy doors, pull out this mangled, melted, blackened piece of metal that used to be a precision drill, and you throw it in the recycling bin.
Yep, it's garbage now.
And then you grab a brand new shiny drill from the tool crib, you load it into the machine. Wow, wait, no. You don't just press start and go back to work, do you?
Doing that will instantly shatter the new tool.
Really?
Yes, and this is a crucial programming step outlined in the guide that highlights the deep physics of machining. When you put that brand new tool in, you cannot go back to your original day one fast speeds.
Wait, why not? It's a fresh, brand new tool. Shouldn't we just start the whole break-in process over again from the top?
Well, the tool is new, but the environment inside that hole has fundamentally changed. You are picking up a cut halfway through a deep hole that was just subjected to massive heat, intense friction, and aggressive melting wear from the dyeing tool.
The hole itself is messed up.
Right. The physics of the metal block have been altered. The metal right at the bottom of that hole is no longer the same soft, uniform steel it was at the surface.
Oh, wow. The dyeing tool actually scarred the metal block. It's not just a rough surface.
The metallurgical term is work hardening.
Work hardening.
Yeah, the intense heat and pressure from the failing tool compress the crystalline structure of the steel at the bottom of the hole, effectively turning that specific pocket of metal into a hardened shell.
Like armor plating.
Exactly. If a new drill hits that work-hardened shell at full speed, it will shatter on impact.
So the CNC program requires major manual updates just to survive the damage the last tool caused.
Yes. The text dictates that the operator must use the speeds from the late normal wear stage as their new baseline.
So already lower than the start.
Right. And from that already lowered number, they must drop the new speed by an additional 10% to add a massive safety margin.
Wow, that's slow.
And they must drop the new feed rate by 7%.
And they have to take smaller cut depths too, right?
Smaller cut depths are mandatory here. You have to gently tiptoe the new tool back into the cut to slowly carve away that work-hardened, damaged layer of steel left behind by the failure.
You really have to sneak up on it.
You do. Only after you've cleared the damage can you slowly ramp the speeds back up.
It is a phenomenal amount of proactive work, math, and attention just to drill a hole in a piece of metal. But when you look at the whole picture, you realize that matching these CNC parameters to the specific, evolving stages of tool wear is the only thing standing between a profitable factory and total financial ruin.
It serves as the ultimate exercise in proactive control. We've tracked the entire life cycle.
Yeah, we have.
You start by carefully mathematically flattening the microscopic bumps on a fresh, fragile tool by lowering the speed 10%.
And then you track that tiny 0.1 millimeter wear mark during the marathon phase.
Right. Dynamically dropping speeds and feeds to manage the creeping heat and friction.
And finally, you have to be disciplined enough to slam the emergency stop the absolute second you hear that screaming, grinding noise, completely overriding all your carefully planned parameters to prevent the tool from melting into the block.
Every single one of those tiny mathematical adjustments prevents drill breakage. It guarantees the physical quality of the workpiece.
And ultimately saves the factory massive amounts of money in avoided downtime and scrap. Exactly. Bringing this highly technical subject directly back to you, listening to this. Even if you never step foot on a factory floor, even if you never see a CNC machine in your entire life, this deep dive is really a masterclass in preventative maintenance for life.
It really is.
It proves that simply pressing start and ignoring a running system guarantees a catastrophic failure. Because everything degrades over time, everything experiences friction.
It is a universal truth of physics, whether you are dealing with a solid block of aerospace titanium or any complex organizational system we manage.
So it leaves you with something to really chew on long after this deep dive is over. If a massive block of solid steel and a highly engineered tungsten carbide drill bit require such precise, constant, proactive micro-adjustments just to survive the friction of their environment.
What's the equivalent for us?
Exactly. What other invisible wear and tear in our own daily lives, our habits, or our businesses are we currently ignoring simply because we haven't heard the grinding noise yet?